University 的谭景辉老师，他继续会给我们讲这个 p-adic 约化里群上的表示。欢迎。
Okay, so I'll start. So yesterday we studied reductive group G by understanding its subgroups, some subgroups. So yesterday we studied maximal split tori. So this is studied yesterday. So for today, we are going to study parabolic subgroups. So some of the topics overlap with Tan Fang Yang's lecture, and also some compact subgroups. Okay. So maybe I give a review, just a very short review of what we obtained yesterday. So suppose we are given a torus T. Okay. So from this we have a root system. And inside we choose a basis and call these roots simple roots. A simple, you can say it is a simple root system. Okay. Then, okay, so we will use these roots to construct parabolic subgroups. Okay. So first of all, we look at the minimal one. So those what we call Borel subgroups. Okay. So what are these? So we define this group B to be T semi-direct product with U, where U is, remember all these U alphas, they are the one parameter subgroups, and I take those alpha in the positive root system. Okay. So you can check U is a subgroup. Okay, so this is usually called the unipotent subgroup of B. Unipotent subgroup. And this B is called the standard Borel subgroup. Okay. So in our examples, if G is the classical groups that I gave yesterday, okay, then B is just the upper triangular subgroup of G. Upper triangular subgroup. Okay. In all those classical groups. And in general, a Borel subgroup is a G conjugate of B. Okay. A G conjugate of the standard one. For example, you can have this one, is B minus, which is, if you remember this, a J matrix. yeah. This J matrix where J is the anti-diagonal matrix. So this is also a Borel subgroup. Okay, so far so good. Yes. So now, in general, what is a parabolic subgroup? So I take a subset theta of the simple root system. So I think in Zhifeng Yang's lecture, this is the set F. Yeah. Okay. So and then I define A theta, which is okay. So I take a root alpha. Remember, alpha is a character from T. Okay, so this kernel is a subtorus in T, and then I take the intersection with all alpha in theta. Okay, and to guarantee this is a torus, in particular it is connected, I take the connected component of the intersection. Okay, so it is a subtorus in T. In particular, you can say T is A empty. And I define M theta to be the centralizer in G of this subtorus. Okay, this notation means the centralizer. And you can check, this is a reductive group in G. A reductive group whose root system. Okay, you can see the centralizer in particular, it contains T. Okay, T centralizes is subtorus, of course. Okay, so I'm talking about the root system of M theta, of T inside M theta. Okay, so this reductive group has root system being those roots lying in the span of theta. Okay, the integral span of theta. Okay. Okay, is it okay? So the root system is just a subroot system of the reductive group G. And I can define this P theta is just M theta, this reductive group, times this U. So this is the standard parabolic subgroup. Associated to the subset theta. Okay. So if I write it in this way, then you can see usually there's a large intersection with M theta and U. Okay. So it's better to write is p theta as m theta times another subgroup n theta, where n theta is defined like this u, but I just take those positive roots not in the span of well, basically this one, okay? The root system in M. Okay. Then in this way, you can check so that M theta has trivial intersection with N theta. Okay? So far, so good? Yes? Okay, I slow down a little bit. So thanks to Peng, I just skipped this example. So for G is GLN, you know how a parabolic subgroup looks like. Okay, so okay, basically P is a block upper triangular subgroup, and M is a block diagonal subgroup. If G is a special orthogonal group, well, actually it is also true for symplectic group and even orthogonal group. Okay, I complete the list. Okay, then again, P is a block of a triangular subgroup. Perhaps I write it in this way. So I just write down M theta. Okay, and you know how P theta looks like. Okay, so M theta is isomorphic to a bunch of GLN. So GLN 1, GLN K cross. Well, okay. Say if I look at orthogonal group or special orthogonal group, then this M theta looks like this. And K, maybe I make this index a K minus 1, okay? That is, this is the K. Okay? So the last piece looks like this, where the sum of all these N1 to Nk, first of all, these Ni, they are non-negative integers. And the sum of all these is N, is N here. Okay. For the others, you just replace this special orthogonal group by these. Okay, similar. And you can check, I leave you to check, okay, whether this Nk is 0. It depends on whether remember the simple root system, okay, is E I minus E I plus 1 with the last one being En. Okay, this one is it looks special to the others. Okay, so whether the last piece here, this Nk, is 0 depends on whether this En is in your choice of theta or not. So far, so good? Any questions so far? Maybe you can give me more feedbacks because I don't know whether you understand or not. Or maybe I should slow down or maybe faster. So far the materials are okay. Yeah, okay. So I should say in general, a parabolic subgroup is a conjugate to these standard ones. Okay? A parabolic subgroup is a G conjugate to a standard one. Okay, so any of these p theta. So when theta is empty, then we know this is the Borel subgroup, and if theta is the full simple root system, then this is G. Okay, so Chung Pang Mok mentioned this, and also you can check. If theta is a subset of another subset omega, so they are both inside of the simple root system, then P theta is a subgroup of P omega. Easy to check. And also this one is a bit different. Okay, so different P theta are not conjugate with each other. Or in other words, that means if you have two different subsets, that implies P theta, maybe put it in the reverse way. So if P theta is G conjugate to some P theta prime, then it implies the two subsets are equal. So as a corollary, the parabolic subgroups in G the G conjugacy classes of parabolic subgroups in G, okay, is parameterized by subsets of the simple root system. Okay. So here I give a nice characterization of parabolic subgroups. And this fact is usually used by algebraic geometry. So a useful characterization of parabolic subgroups. So it says that P is a parabolic subgroup in G. If and only if G mod P, viewed as an F variety, is complete. Okay. So this is a definition in algebraic geometry. So I won't give the full definition, but let me say consequence of this is that already here, okay, in particular G mod P is compact. Okay. So this consequence is useful later on. So let me give an example for you. By the way, so this variety is usually called flat variety. Okay, usually called a flat variety.
When you say G mod P is compact, you mean F point?
The F point is also compact. Yes. Yeah. But as a F variety, this is.
But when you
also
say
compact.
G mod P is compact, you mean the not as a variety, as a top,
Well, yeah, I think both are correct. I mean, well, the F point, the F point of this is just this, right? Anyway, I mean,
and your F is a local field.
yes, I think. Well, okay. First of all, I think this is true, and of course, so is the subgroup, the Galois fixed points.
Okay.
Is it correct, or you have other things in mind?
No, because when you say compact, is you take the F point.
Oh, you mean the topologies
Yeah,
different?
It's a variety. Then of course you say it's complete. You say compact, you refer to
Okay.
topological space different from F point.
Okay. I think both are correct.
Okay.
Any other questions? Okay. So let me give you this simple example. So in GL2, you let this group acts on a set of lines in, well, depending on which field you are taking. So maybe I use a field K here. Okay. Okay, so of course GL2 acts on K2 just by multiplication. So it acts on the set of lines. Okay, just a one-dimensional subspace in K2. Okay, just by multiplication. So what are the lines in K2? So you can have a line with some slope, okay, that is given by the scalar K. Or you can have the vertical line that is slope infinity, if you imagine. Okay, so that means the lines in K2 you can imagine is like bijective to the set K with the vertical line whose slope is infinity. So if you know about a little bit about algebraic geometry, this is the projective line with scalar or over the field K, the projective line. And in particular, this is compact. It is compact. It's the line compactified with a point. Say if K is the compact field, then this is the Riemann's field. Okay. And then you check the stabilizer. Well, sorry. First of all, Gx transitively. I should emphasize Gx transitively. If the action is transitive, then you check the stabilizer. The stabilizer of this vertical line is the Borel subgroup B. That means G mod B is bijective to this projective line. Okay, in particular, well, this is an isomorphism. So G mod B is compact. Okay. Okay, so is it good for the example? This is compact. And another fact about parabolic subgroup is the Broussard decomposition. The Zhifeng mentioned a special case, and here I will give a more general statement. So first of all, subgroup of the normalizer, not G, but in this M theta. I think this maybe you can this M theta. So this M theta is called the component. So you can write it when I define this up. This theta is a name called the Levy component of E theta, or sometimes I'll just say the Levy subgroup. Okay. So it's a subgroup in G. So that means W contains this normalizer. Let me denote it by W theta. So we have a lot of subgroups in the W level. So Broussard decomposition tells us that if we have two subsets, theta and omega, then there's a bijection between the double coset generated, the double coset defined by p theta and p omega of G to the double coset of W defined by W theta and W omega. It's a bijection. And this bijection induces decomposition, so that G is decomposed into double cosets P theta, P omega. You can take a lifting. So this W is an element in W. You can lift it to G. So say W dot is the corresponding lifting. Then you can use it to represent double coset in the decomposition, okay, with W in the double coset of W. And in particular, if theta and omega are empty subsets, then these are trivial subgroups. Okay, these two are trivial, and then these two are Borel subgroups. So this becomes the statement that Tan Fang Yang wrote this morning. So this is a bit more general. So I will go into compact subgroups, and before that, let me see if you have any problem about parabolic subgroups. Okay, should I move on? Yeah. Then I'll talk about some compact subgroups in G. And for the purpose, now I take F to be a p-adic field. So I'll review what a p-adic field is. So I'll define a range of p-adic integers. Okay, this set P. Wu Chenyan mentioned this before, so I'll just go through it quickly. Okay, so this is just a range of formal power series in P with AI in 0 to P minus 1. Okay, the coefficients AI. So this is the same as what we can define it. So this is the inverse limit of P to the K set. Okay. same thing. And the field of p-adic numbers is the field of formal Laurent series in P. So it starts from somewhere at K. So this K can be any integer. And again, the coefficients are in the set 0 to p minus 1. Okay? So don't mind if the number blows up. Okay? So they are just formal things. And I'll define a topology on it so that the numbers that you think they're blowing up, but actually they converge to some number under this topology. So the topology on QP is defined by the norm. So this norm, if you input any p-adic number, if the first term is kth term, that means k is non-zero. Okay, then the length is p to the power minus k. Okay, so you have to be careful, a minus sign here in the power. That means if you take a large power in p and its length is small. Okay. So that means this power series, this Laurent series actually converges. In a Cauchy sense, okay, you can check. So here is an exercise. You can check using this topology. Set P is an open and compact subset. So in particular, it's open and closed at the same time. Okay? So it's quite different from the real case or the complex case. Okay? So it's open and compact. And of course, it's also true for any ideal of set P, for any principal ideal, I should say. Okay, so it's this ideal. It's generated by any power of P. These are also open compact. That means QP has a system of open neighborhood around 0 given by these ideals. Inside QP, which are in particular they are compact ideals. And you cannot find such a good neighborhood in the real and complex case. Okay. They are at the same time compact and ideals. Okay. In particular, they are additive subgroups. similarly, you have a system of open neighborhood for QP cross. Okay, QP cross, if you don't know the notation, it's just QP minus the 0 point. So this is the multiplicative subgroup. Okay. It has a system of open neighborhood, but now it's not around 0. Okay, 0 is deleted, so it's a neighborhood around 1. Okay, so what is this? Under this, we have set P cross, which is also open compact. And inside this, we have 1 plus P set P, okay, 1 plus the ideal. You can check this inside set P cross. By the way, don't get confused, okay? This set P cross is not set P minus 0, okay? Set P cross is the invertible elements in set P. Okay, that means if X is in set P, then its inverse, the inverse in QP, is also in set P. Okay, so this is set P cross. And you can check 1 plus the ideal. Actually, this is the maximum ideal. Okay, the ideal generated by P. If you add 1, then it is invertible. And of course, 1 plus the ideal of P squared. Okay, all these contain 1, so it forms these subgroups form a system of open neighborhoods of 1. These are compact subgroups. Perhaps if I write it in this way, then this is more interesting. The set P is all the elements which has norm less than or equal to 1. Then you can imagine this set P is like a disk. Okay, so it's open, it's compact. Okay, it's also open because the its norm is a discrete norm. So it's open and compact. And also for this one, this is all the elements with length 1. Okay, so this is like a circle in QP. So this is also compact. Okay, so you can see in the fields we already have a lot of compact subgroups, a lot of interesting ones. Okay, so this structure will be brought to the reductive groups. Okay, so compact subgroups. Okay, so perhaps I can give some examples in the general inner group, okay, to get a sense of how compact subgroups look like. Okay, say in GLN we have this kind of subgroup. So this, I use the symbol K0 to stand for I write it this way. All the invariable matrices with integral entries. Okay, so invertible matrices with integral entries such that its inverse also has integral entries. Okay, so inverse also has integral entries. Okay. Roughly speaking, you just think about such a matrix as integral entries. Okay, everything is in set B. And whose inverse is also in looks like this. Okay. K0, and here are some other ones. K. Okay, this little k. Well, okay. Okay, this is capital K. This is little k. Little k is an integer. Is equal to the identity matrix plus all the matrices with entries in the ideal generated by p to the power k. Sorry, k has to be positive. Not set, but n. Okay. So you can check this is a subgroup in K0. And you have a chain that forms a system of open neighborhoods around the identity element in GLN. Okay. Maybe I emphasize GLN QP. So here are some other examples. I have I0, which is all such elements with the entries in the lower triangular part. So here I has to be greater than J. All these lies in P, set P, okay? The ideal generated by P. So in picture, it looks like in the upper triangular part, they're still well in the ring set P, but in the straight lower triangular part, they lies in the ideal. The ideal of multiples of P. So this is another kind of compact subgroups, not in this list. You have another one here. I write it IK, which is I plus I use too many i's. Sorry. I still use the symbol I. Okay, but this I is the identity matrix. This I 1. Sorry, I mixed up my notations. Okay, let me be careful. Okay, what if I just bold all the i's for subgroups? Okay, so I0, IK, and this is identity matrix. But this one is, and I do, let's see, I use J maybe. Okay, sorry about the confusion. Okay, this J is the set is a set that looks like this. Okay, so in the lower triangular part, the entries are in the ideal of multiples of P, and only in the straight upper triangular part, the entries can be in set P. And I take the kth power of this set J, and you translate it by an identity matrix. You can check this is a subgroup in I0. Okay, and you also have a chain that forms a system of open neighborhoods around the identity matrix. And of course, because every entries is in some ideals of set P, so all these subgroups are compact. Okay, so we have a lot of compact open subgroups. I think I will skip some of the things that at the end I give a construction. Let me see. Okay, perhaps I'll skip the construction and tell you the result straight away. Okay, so here's so I'll just tell you the result. So there exists some good compact open neighborhoods of the unit element in any reductive group G. So maybe I should say G is a reductive group. Okay. Let me be consistent with my notation. Okay, so I'm talking about the F points of a reductive group. So there exists some good compact open neighborhoods of the identity, okay, satisfying the following conditions. Okay, so there are two conditions. One is called Iwahori decomposition. Which says that if you have a standard parabolic subgroup, okay, I just write it in this way, so standard parabolic. Okay. So implicitly, it depends on the subset theta of the simple root system. Okay. So if it is a standard parabolic, then I forgot to write down the notation for my open subgroups. Okay, so these are the Ki. Okay, just a sequence of compact open subgroups, such that for any parabolic, the product map from so it's a triple product from each Ki intersect with N, M, and maybe I put it in this order. Okay, so it's a triple product with Ki intersecting N minus, M, and N. Okay, this N minus is the opposite of N. Okay, remember this M is like a block diagonal subgroup, and N is concentrated here in the upper triangular part. Then so this is N, and N minus is here. Okay, and M is in the middle on the diagonal. Then you expect these N minus M and N occupies the whole thing. Okay, and is true for this compact subgroup Ki. This product map is a bijection. Okay. In the group level, you can say this triple product goes to a dense subset of G. But on the compact subgroup level, because it's compact, so this dense image is just the whole compact subgroup. Okay? But you have to choose Ki to be good enough. Okay? So here are the some examples of good compact subgroups. And 2. Okay, so this one, I'll just write it down, okay? So, because okay, right here. So this will be the last slide. So if A in the subtorus A theta is positive, okay, in the sense that if you put A in any root, any simple root, not in the set theta, this element, okay, this, remember a root maps an element in, so in this case, A theta to the field F. So you can measure this element by taking the norm on F. Well, sorry, F is just QP in this case. F is QP, so you can measure the length of alpha A. If it is less than or equal to 1 for all alpha, not in theta, then we call it positive. It depends on the subset theta, okay? But A is already in A theta. Then, if you conjugate the n part of your compact subgroup by A, it lies, well, it normalizes this, sorry, not normalized, but okay, it's a subset of it, okay, like this. And you can say something similar for the n minus part, but here you have to conjugate it by A inverse. Okay, like this. So roughly speaking, what it means is if you have an element that, okay, so say if G is GL2, so there are not many choices for theta, right? So you can just take the E1 minus E2. Then say if A looks like this, so P to the power C, P to the power D, where C is in this case is greater than, okay? C is greater than D. Then you let this A to conjugate the n part of a compact subgroup, say if it looks like this. So you get P to the C minus D X. Then you ask whether this element is still in the compact subgroup. Say if X is in, say P to the K ZP, you ask whether this is still in P to the K ZP or not. Then this condition guarantees this is true. Okay? So that's the meaning of this. Okay, so I'll stop here, and tomorrow I'll go into representation theory. Questions? Maybe a bit technical today, but the facts will be used later on.
You we can also discuss during the discussion session. All
Okay. I think now is also a good time for discussion. Any questions are welcome.
complete variety 那个定义怎么定义？完备 variety。
对
complete variety。
complete variety
那个定义 complete。
定义是它是一个separated scheme over geometric field something like that. Also projective variety.
projective 的是 complete。
Projective is complete.
是完备的是吧
I think complete is projective. Or maybe equivalent. I forgot exactly. 这是一个代数几何的概念。
对，我忘记了。它是不是就是类似于紧凑的